Hi, welcome to this talk as part of the learning workshop in stochastic analysis. So in this workshop, you've had a mini course by Thomas, which included stochastic differential equations, even in infinite-dimensional settings. So when all the processes takes value in certain Banach spaces. And then you will have a talk by Ed that introduces you to the FEYNMAN-KAC formula that relates stochastic differential equations to PDEs and show how you get properties of one from properties of the other. So what I want to do with my talk is introduce you to one of the methods one can use to actually solve stochastic differential equations. And this method is called the Doss-Sussmann transform. What it does is that it turns an equation about a process X, which really is an integral equation involving a Lebesgue integral and a Ito integral, into an equation for a process Y that only involves a Lebesgue integral. Right? So you're fundamentally reducing the difficulty from a difficulty that includes stochastic integration difficulties to a problem that does not involve any stochastic integration, although obviously it still involves stochastic processes. Now, there will be three parts to the talk. In the first one, I will show you the original Doss-Sussmann arguments. They obtain the same result independently around 1977. And that's in the context of a classic one-dimensional or multi-dimensional but finite-dimensional SDE with fairly smooth coefficient. What I mean by fairly smooth is, let's say that sigma is C11 and B is Lipschitz. Now, this idea recently has regained a lot of popularity. So I will tell you about two of the modern instances of the Doss-Sussmann approach to solving SDE. One is a paper by Karatas and Roof from 2014. And in this paper, what they do is that they look again at the classic finite-dimensional problem, but it's not that classic because they really drop the regularity assumption on sigma and B. And I'll tell you how they do it and how far they push it. And then in the last part of the talk, I will tell you about a very recent preprint from May 2021 from Ben Goldys and FEYNMAN-KAC. And this is looking at a problem in infinite dimension on the space of bounded linear operators acting on a Hilbert space. This is a linear problem, but this is already very difficult to solve because there is no stochastic integration theory on B of H. But we'll see how this can be attacked through a Doss-Sussmann approach adapted to this problem. Now, word of warning, I'm going to be reasonably precise in the first part, but then when I talk about the more recent variations of Karatas and Roof and GOLDYS-PESZAT, I'm not going to do their papers justice at all. I'm going to hide all of the technical difficulties. All I really want to do is show you what a Doss-Sussmann transform look like and how one might go about finding one that is appropriate to the problem that you might be interested in. And note that in recent years, they have been used in a variety of problems: linear, non-linear, PDE, SPD, finite dimension, infinite dimensions, rough or not rough. This is not tied up to a particularly specific concept. It's more of a philosophy of reducing the problem that involves both a deterministic and a stochastic integral to a problem that only involves a deterministic integral, albeit a deterministic integral of stochastic processes. Okay, let's have a look at this third theorem due independently to Doss and Sussmann. So this theorem works under fairly standard assumption in SDE theory. So we have a C11 volatility coefficient sigma that happens to be bounded and has bounded derivative. And we have a drift term B, which is Lipschitz continuous. And we're looking at this SDE. Now the point of the Doss and Sussmann theorem is to turn this SDE into an ordinary differential equation. So move from an equation about X that involves both a Lebesgue integral and an Ito integral to an equation about Y that only involves a Lebesgue kind of integration. Now, in doing that, there would be a function f that we need to determine that tells us which equation y satisfies. And then once we found the solution to the equation for y, we have another function u that needs to be determined that tells us how you reconstruct the solution x of the SDE you started from. Now, why is this useful to turn an equation that involves ds and dws to an equation for a transformed process y that only involves dt? Well, for starters, this gives you a pathwise approach to solving the equation. That means you can fix your probability variable omega and solve this equation here for every value of the probability parameter. And then you feed that back to here and you get your solution process xt evaluated at the point omega in your probability space. Now, you cannot do that if you solve this equation directly, say, through a fixed point argument in an appropriate space of processes. That's because if you remember the construction of the Ito integral, the construction of the Ito integral involves looking at every value of the probability parameter, right? And it's a construction in L2 over the probability space. So here, this advantage you could see would be very good if you want to do, say, numerical analysis of the solution, because you can fix an instance of your probability variable and then you can solve for that particular value rather than having to do something for every possible value before you can say anything about your solution process. Now, from a more theoretical point of view, this is also very helpful because here, if you solve directly, you have the difficulty, especially when you go to rougher coefficients than that, of making sense of the stochastic integral. Whereas through this approach, all you really have to do if you're dealing with particularly rough situation is to be able to manage them at the level of an ordinary differential equation. And then you will use that to give an appropriate meaning to the solution of the equation. We'll see a bit of that later. Same thing, if you go to infinite dimension, you might have the problem, and you really do if you're in a Banach space that is not a UMD Banach space, that you might not have an appropriate stochastic integration theory, like the Ito integration theory. On the other hand, you have the Bochner integration theory. So you have an extension of the Lebesgue integral to Banach space valued function that works in quite a variety of situations. So either because you want to go to infinite dimension to treat SPDEs or because you want to go to things that are a bit rougher than that, as we will do later, having an approach, philosophically speaking, that should work in this way and reduce the problem from SDE to ODE can be extremely helpful. Now, I'm going to show you the proof of this, or a very short sketch of the proof of that. But I just want to point out before I do that, that this is the sort of mirror opposite of another approach to solving SDEs, which would consist in removing the drift. So what one can do sometimes is change the Brownian motion in a way that incorporates the drift term, such that we turn this SDE that involves both DS and DWS into an ODE that only involves DWS. So that's called the method of removal of drift. And this is particularly helpful if you want to handle sigmas that are still reasonably nice, but B's that are not. Now, there's a subtle difference between the two that I'm not going to talk about much in this talk. It's the notion of strong versus weak solution in the probabilist sense. So strong means that we have a fixed probability space with a filtration and a Brownian motion on it, which is our noise. And then keeping that fixed, we find an adapted process that satisfies the integrated version of that almost surely. That's a strong solution. A weak solution, we would allow a change in the probability space, the filtration, and the Brownian. And maybe that will be using that drift term in order to create that change. Now, that's not the purpose of this talk. What I really want to show you is how you come up with functions such as U and F and realize that a reduction of that kind is possible. So let's see how one can prove such a theorem. What you do is you assume that xt is of the appropriate form. So it's a function of bt and yt, and that yt is of the appropriate form. So it satisfies an ordinary differential equation of this form. Now you apply Ito formula, right? And Ito formula tells you that dxt has to be dx upt yt dbt plus the term involving the second derivative in x and the quadratic variation of the Brownian, so that gives us a dt, then a term involving dy of u bt yt, and that's the term in dyt, and there's no term involving quadratic variation of dyt because we assume that it satisfies an ordinary differential equation, so we'll have quadratic variation 0. Now, in order for this SDE here to really be the SDE we started from, this will impose condition on U and on F, right? Remember that the term we have here, dyt, is f bt yt dt. So what have we got? Now, from this first term here, we're going to need dx of u to be equal to sigma of u. Now that's just a condition on the function u that appears in the transform. Now, once I've assumed that, I'm also going to get, for free somehow, that dx squared of u is sigma prime of u times sigma of u. So the term that I have right here is going to give me the 1/2 sigma prime of xt, sigma of xt dt. So now the only thing that I really require is for dy of u times f of x y to be equal to b of u of xy, right, for all x and y in R. If I require that, then I would have that xt satisfy the SDE I started from. And the way you require that is just by definition. So you want to define f to be equal to b composed with u divided by dy of u. And that's your definition of the transformation f. Now there's a few things that you need to verify. You need to verify that dyu is never 0, and that's not too difficult to do. You start from this PD, you find out that this has to be an exponential of something. We're going to need to impose some initial condition on this equation, and one that is quite convenient is to assume that u of 0y is equal to y for all y in R. And that's natural because it tells you that if you had no noise, then your SDE would be purely the ODE for y. And then with this condition, you find that everything is well defined, the u and the f, and you will find that the ordinary differential equation that we've defined here has indeed a unique solution, because you can check reasonably easily that f is Lipschitz continuous and satisfy standard gross conditions in the theory of ordinary differential equation. So that's just the idea. You apply Ito formula, you hope for the best that your dream of solving the problem in this particular way actually will work, and you find out what u and f needs to satisfy, and you realize that you have a PD for u here and an expression for f there that uniquely define u and f, provided you add some initial data, and gives the appropriate regularity to f. So we have a nice way of solving this stochastic differential equation as long as sigma is C11 and b is Lipschitz continuous. But what if we want to treat less regular coefficients sigma and b? Now I'm going to have a little interlude to tell you why you might want to treat less regular coefficients. And for me, that comes from the FEYNMAN-KAC formula and the desire to solve deterministic PDEs. So if you look at this deterministic PDE, a diffusion parabolic problem, so dtu equal a non-divergence form operator here plus a drift term. What the FEYNMAN-KAC formula gives you is a way to link the solution to that PDE to the solution to this SDE. And the link is this beautiful formula. U at Tx, the solution of the PDE, is the expectation of the initial data at a point which is given by the solution process started at x at time t. Now, the fact that we have a well-posed theory for the SDE that requires such regularity, Lipschitz on B and C11 on sigma, for this SDE to be well-posed, will impose, through the FEYNMAN-KAC formula, the same regularity condition on the term sigma and b here. Now, this is a little frustrating because, in general, in PDE, one can solve this type of equation under much less stringent regularity assumptions. For instance, if we look at a PDE in divergence form, dtu equal div a grad u, then you can use energy method and you can solve this equation under just an L infinity assumption plus uniform ellipticity assumption on the A. Now, if you rewrite that as a non-divergence form problem with a drift, then the drift will arise as the derivative of the coefficient in the divergence form equation. So if we have a theory that requires A prime to be Lipschitz, then we're really only solving the divergence form equation for C11 coefficient. So it would be really desirable to be able to deal with much rougher A, ideally a L infinity. Now, this is certainly not accessible at the SDE level with current technology, but we can nonetheless go substantially below a C11 assumption. And I'm going to show you how Karatsas and Rueff did something like that using a Doss-Sussmann approach in 2014. But before I do that, I need to do one more interlude and show you how the Ito formula can be extended to deal with such rough functions. And this is called the ITO-TANAKA formula, and this works for convex functions, because for a convex function you have a left derivative, and you can define a measure that will charge an interval in the following way. Take the left derivative of f at point B minus the left derivative of f at point A. Now, with this definition, you have an Ito formula that involves this left derivative instead of the standard derivative, and instead of the term 1/2 integral of f second of the process ds, you have this integral involving the measure that replaces the integral of the second derivative and something here called the local time associated with the Brownian. And the local time is defined in that way. If you integrate it against a characteristic function, you get up to a factor 1/2, which is natural because this term should be 1/2 of an integral of the second derivative. The integral of the indicator function of the Brownian integrated between 0 and t. So the way you should think of this quantity is that it measures the time that the Brownian is spanning in the interval 0t in the interval AB. And this density here gives you a formula that generalizes the quadratic correction term in the standard Ito formula that would normally involve the second derivative of f. Now, unsurprisingly, the way you prove this formula of Tanaka from the standard Ito formula is through approximation. So you take a sequence fn of smooth function that approximate f uniformly, and then you do that in such a way that the fn prime pointwise approximate d minus 1 of f, and you do that in such a way that fn second of x dx as a measure converges weakly to d mu f. And then if you look at the formula defining the local time, you can extend it such that tested on fn second, what you get is 1/2 of the integral from 0 to t of fn second of ws ds. And this is the term that appears as the second order correction term in the standard Ito formula. Now, using this Ito-Tanaka formula and a lot of fancy technical work that I will hide here, Karatsas and Rueff in 2014 managed to generalize the Doss-Sussmann approach to a much rougher class of coefficients. And so what they look at is the following. They have a Ito term, which is the same as what we had at the beginning of the talk, but then the drift term, which for us was just the integral of b of xt dt, with little b being even Lipschitz continuous, is now a much more general Riemann-Stieltjes integration against a process that is continuous and of bounded variation on compact Z. So this could typically be the integral of some little b of xt dt, but the little b certainly doesn't have to be Lipschitz continuous. And if you remember, we had a term sigma prime of xt, sigma of xt dt. This is now generalized in the way it has to be given this roughness here and there to something involving the local time associated with x. And the difference between that and the local time associated with the Brownian we've seen before is that in this more general situation, you have to integrate against the quadratic variation process of x. In the case of the Brownian, this would just be ds. But just think of that as being the appropriate analog of the term involving integral of sigma prime of xt, sigma of xt dt. The point is that our sigma is not much rougher, and the analog of our little b is not much rougher. Our rough, well, all we ask from sigma is that log of sigma is left continuous and of bounded variation on compact set, and all we ask from little b, if you want, is that once you integrate it, you get a continuous process of bounded variation on compact set. So this is much, much rougher than what we've seen before, and nonetheless, we are about to see a Doss-Sussmann formula. So here it is. We need a function h that is defined as the integral up to x starting at a point c of 1 upon sigma. And then from the assumption, we get that this function h has an inverse, and we denote the inverse function by theta. And then we have a formula involving theta and h to construct the solution of this SDE, or more precisely the stochastic integral equation, from the solution of an ordinary integral equation that is given here. So we still have this integration in the Riemann-Stieltjes sense, but now we don't do any stochastic integration. We just plug in the Brownian and a function of the Brownian involving the solution of that integral equation and this function theta, which is constructed from the coefficients. Now, let me give you a very quick idea about the way this is proven. So you introduce a process here, yt, and you apply ITO-TANAKA formula, but not associated with the Brownian, associated with the process y. And what this gives you is x of t equal x naught plus integral from 0 to t of theta prime of x naught of ys dys plus the local time term, which is local time associated with y at the point little y d theta prime of x naught of y, integrating over r. Now, because of the way theta is defined, what you have here with your theta prime x naught of ys is actually sigma of theta x naught of ys, which is exactly xs. And then you have your dys, which is two term, a dws term, which is exactly what you want, and then another term, which is d of h of x naught c dot, if you want to apply it s. Let's put it that way. And now d of h of x naught of c, because your c has to satisfy this equation, that will give you precisely the script b of s w theta c dot of w. So you get the appropriate terms here and there from the ITO-TANAKA formula, and now you have this term involving the local time, which is also going to give you that term involving some fairly technical work with the local time and the way theta is defined. Now, to finish, I want to show you some very recent work of Ben Goldys and FEYNMAN-KAC that's on arXiv from May 2021. And this is about a much simpler equation. This is just a linear equation, but the catch is this is a linear equation involving Hilbert space valued processes. And what we want to do is solve this equation by having what's called a stochastic flow or an evolution family for this equation. So a family of bounded linear maps that map a data at time s to a solution at time t. Now, the difficulty is that we cannot just solve an SDE in the space of bounded linear operators acting on an infinite-dimensional Hilbert space, because there is no stochastic integration theory in that space. So the Doss-Sussmann approach is going to be very helpful in that context, because it's going to reduce the stochastic integration problem to a problem that only involves ordinary differential equations, which we can certainly solve in the space of bounded linear operators on a Hilbert space. So here are the assumptions. So all my processes are valued in a Hilbert space H, and my operator A here is linear, but it generates a C0 semigroup on H. So this is really just an abstraction of what you will have from studying partial differential equation and then stochastic partial differential equations. So you should think of this part as modeling a PDE, where the Hilbert space is L2 of something, and A is, say, the Laplacian on that space. And now, we don't want to have just one-dimensional noise, just use one Brownian here, because we are in infinite dimensions, so we'd like to add noise in every possible direction. So we do that by having a sequence of independent copies of the Brownian and having operators BK, bounded linear operators, that inject that noise in all of the directions of our Hilbert space. Now, for summability reason, we have to put some assumptions on these families of operators BK, and we're going to operate under the fairly simple assumption that the sum of the norms of BKs as bounded linear operators is finite. Now, the way the noise is going to appear in my Doss-Sussmann transform is not through just a function of all these infinite copies of the Brownian. It's going to be through a function of a certain evolution family that you get from solving that SDE, not in B of H, but just in H. And that SDE involves the terms BK, and it involves the terms B naught, which is constructed from the BK in that particular way. Right, so this here will give me a family of bounded linear operators indexed by T and S with T greater than S, and we're going to use that to plug into our Doss-Sussmann formula. So now that we have the noise, here is the ordinary differential equation that we're going to need to solve to reconstruct the solution of our SDE using the noise and the solution of an ODE. That's the Doss-Sussmann philosophy. So this is an ODE in the space of bounded linear operators on H. it has the identity as initial data, and what you have is almost what you would guess, which is an ODE involving A minus B naught, but you need to conjugate that using the evolution family that help you define the noise. But also you need to approximate A by bounded linear operators, because A itself can be unbounded. So you do that using Yoshida approximate, you give yourself a positive lambda, and you replace A by lambda A times the resolvent of A at lambda. Now this converges to A as lambda goes to infinity, and so we have these families of ODEs in the space of bounded linear operators that will have solutions which are bounded linear maps G lambda TS. And then these families of map G lambda TS happens to have a strong operator topology limit as you send lambda to infinity, and that is going to give you a family of bounded linear operators, which is the solution of the ODE part of your Doss-Sussmann approach. And that's pretty much it. Once you have the solution of your ordinary differential equation in B of H, and you have the evolution family that comes purely from the noise, that's script Y, you just multiply them, and that gives you an evolution family that solved this stochastic differential equation in the Hilbert space H. Now let's finish by having a quick look at why that might be true. So this is done weakly. We look at d of G lambda TS applied to some x, and then on the other side we have y TS star applied to some y, and we take the inner product in our Hilbert space. When we differentiate the left-hand side of that inner product, given the equation, we get y TS minus 1. Let's call this a lambda minus b naught applied to y TS G lambda TS of x. And then this is tested on y TS star y. And then when we differentiate the right-hand side, I should say ds. And then when we differentiate the right-hand side, we get G lambda TS of x, y TS star, sorry, B0 star of y ds. And then we get the sum of a k of the terms that involve bk, y, t, s, g lambda t s x y d w k s. Okay, and then what you have to realize is, first of all, this cancel with that. I've already done that in here, and then we have that the term with the minus b naught here is no cancel with this second part, and when we send lambda to infinity, we get the solution to our equation. And that is the reason why such a formula works. Now, one thing I want to point out with this formula that I find very interesting is that although we start with an equation which coefficients do not depend on time, the coefficients a and b, in order to solve that SDE with time-independent coefficient, we end up solving an ODE very much with time-dependent coefficient. But we've shifted the difficulty to a difficulty that does not involve any difficulty coming from stochastic integration. All the stochastic integration are plugged back into our solution via the evolution family y of ts. So this concludes the talk, and I hope that this has given you a good first taste for the Doss-Sussmann approach to solving stochastic differential equations by reducing them to ordinary differential equations. The take-home message is that in a whole range of problems, you can find a Doss-Sussmann transform, and you can run formal computations to guess what it has to be. Now, of course, moving from formal computations to actual proofs, you will have to overcome a range of technical difficulties, and unfortunately, in stochastic analysis, these difficulties are really minor. Things like defining an integral, approximating objects in the right way, that can be really tricky. But the good news is you can often shift the key difficulty from one field of analysis to another field of analysis. So what I'm really hoping is that these talks will have given you motivation to bring your expertise to stochastic differential equations, because whatever your expertise in analysis may be, there's bound to be a problem in stochastics that could use exactly that expertise. So I'm going to leave you with that, and many thanks for your attention.